Okay, so I'm going to talk about the first part, Chapter 5, which is discrete probability distributions. And a couple things to bear in mind. I'm kind of a creature of habit when I test people on this. So this table here demonstrates a discrete probability distribution. It's discrete because there's a countable, in this case, a finite number of outcomes that can occur. In this case, there's 5 different outcomes. And when I see something like this, I think of those little spinner games you play, like in elementary school, where you have different colors and parts of a circle, and you spin it, and it lands on a number or a letter or whatever. So I always kind of picture that. So when you see one of these, I almost always leave one of these cells with the probability blank. Now, just to make sure I'm understanding, and you're understanding, like right here, I have probability of 0. That's what this means. I could say probability x equals 0. I could write it in words, whatever. But the probability that the outcome of 0 occurs is 0.1. Probability of a 1 occurs is 0.1. Probability 2 is 0.2. Couple things. These all have to add up to 1. So if I were to leave one blank, I'm expecting you to know that they all have to add up to 1. So you would have to add up the others and subtract from 1 to get the missing part. And I invariably ask that. I'll probably be on the quiz over this. Here's some different questions I'll ask. Probability of 2, okay, 0.2. Probability of 5. Well, there is no 5, so that can't happen. So you always want to put 0. You don't want to write cannot happen. I want a numerical value. The probability of something that cannot happen is 0. Probability of something that will always happen is 1. Here's another one. Probability of a 1 or a 3. Well, 1 is 0.1, a 3 is 0.3. So probability of this or that, can't be both at the same time in this. It's this or that. It's 0.4. Another style, probability that 1 is less than x is less than 4. So that kind of means it cannot be the 1 or the 4. It can only be these two. That'd be a 0.3. Another one I could ask that I don't have written on here is what's the probability of a 1 and a 3? That's a trick question because and implies it has to be both at the same time. It's not happening. It can't be a 1 and a 3 at the same time. So this is a basic discrete probability distribution. And again, it's discrete because these numbers are countable. In this case, finite, but they could go on to infinity. When you look at later distributions with the Poisson, there can be an infinite number of outcomes. But there's a discrete number, meaning you could actually sit there and count. There's an order to it. Now, well, this looks scary. Expected value. There's a formula in the book. It's a nice little summation symbol. I love that stuff. But in reality, to find the expected value, all you're doing is taking the value times the probability of the value and adding them up. That's the most basic definition. There's some others, but for what you're typically going to do in a stats class is find the probability that way. Now, I want you to look at this and write it down, whatever, because I'm about to scroll back up to here. It's coming from this table. When I say expected value is the probability of the value times the value, this is where they're coming from. You would take the 0 times 0.1, the value times the probability of value, plus 1 times 0.1, plus 2 times 0.2, plus 3 times 0.3, plus 4 times 0.3. And you write those all down. Here I have it written out. Here I have it with the numbers. And when you crunch it all out, you get 2.6. And that's equal to mu, the mean, or the expected value. And there's different ways this could be written. The expected value is the mean of the probability distribution. And like it says right here, 2.6, scrolling back up, 2.6 isn't one of these values, but it's an average. And what that is meaning is if I play this game a lot, and if these probabilities are true, I'm going to average an outcome of 2.6. So that means a lot of times I'm going to get a 3, a lot of times I'm going to get 4, less likely to get a 0 and 1. But when I start averaging those outcomes, 2.6 is the most likely to occur. It's an average. Okay, it's just an average. That tells me if I play this game 100 times, well, I take 2.6 times 100 and get 260. That would be my average outcome overall. Or that would be my total outcomes overall. And go through your book and read some examples on what's going on with these in the homework problems. And the reason I give you a lot of homework problems on this is I want you to get a handle on how to find it. StatCrunch is of no help really with this. Just use your calculator and know what it means. It's an average. Now I'm going to scroll down here. Standard deviation. So if we could find a mean of that distribution, we can also find a standard deviation. The book has one formula. It's fine, lovely, but I prefer this one here. Sum of the value squared times the probability of the value. You're going to sum that all up minus the expected value squared. Now, if you look at the example, I've just copied the table down here. I'm saying take this value and square it times that, plus this value and squared times that. 2 squared times this, 3 squared times this, 4 squared times this. That's what's happening right. Come on, work with me here. That's what's happening right there. That's the sum of those, minus the expected value squared. Expected value is coming from right up here, this 2.6. I will always ask this on a quiz, and I will ask it on your first test. You have to be able to go through this process. This gives you the variance. Once you have the variance, as with any variance, if I take the square root of it, I'll get the standard deviation, in this case of 1.28. So this is a question that I just want you to be able to follow the process. I'm testing you, can you follow the process? Up here, you have to be able to follow the process, and I want you to have kind of a handle on what this actually means.